In this video, I'm going to talk about the alternating series test and show you how to prove it. So first of all, let's define an alternating series. An alternating series is something like this. A1 minus A2 plus A3 minus A4 plus A5 minus A6 plus dot 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 plus negative 1 to the power n plus 1 an plus dot dot dot. So this is what an alternating series is. We kind of want to find out the convergence or divergence of this series. Basically, we want to find out whether it converges. Now, an alternating series will converge if it has the following properties. Okay, so first, let's go ahead and use a different color. So, number one, each of these terms, an, is positive, meaning greater than 0. Number two, limit n approaches infinity, an is equal to 0. Number three, a sub n is greater than or equal to a sub n plus 1. So let me kind of elaborate on these things. So each of the terms are positive, right? Excluding the signs, okay? Signs alternate between positive and negative. And the limit of the individual terms is 0. That means limit n approaches infinity, an is equal to 0. And an is greater than or equal to an plus 1. That means as you go forward, right, the terms get smaller and smaller, excluding the signs. So don't worry about the signs. It's just the value of the terms. So a5 is going to be bigger than a6. Of course, a6 is going to be bigger than a7, and so on and so forth. Again, ignore the signs, okay? So if these three things are satisfied, by the way, then an alternating series converges. So that means if your alternating series is S is equal to A1 minus A2 plus A3 minus A4 and plus keeps going, then S converges. S converges. If these three conditions are given, then the alternating series converges. Now let me kind of formally show it to you. It's not too hard. So let's find the partial sum. We are going to create a sequence of partial sums, as you know how partial sums are defined. Okay, so let me just remind you in case if you forgot, Sn is equal to A1. In this particular example, is going to be A1 minus A2 plus A3 minus A4 plus dot 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 plus negative 1 to the power n plus 1 an. That's the partial sum. Okay. Now let's create a partial sum for S2, which is going to be A1 minus A2. How about S4 is going to be A1 minus A2 plus A3 minus A4. Now A1 minus A2, I need to put a 1 here. A1 minus A2 is nothing but S2, right? We just found it here. So my S4 is going to be S4 is going to be equal to S2 plus A3 minus A4. Now A3 minus A4 is positive or greater than or equal to 0. All right? Is positive or greater than or equal to 0. Now, look, if that is the case, you can safely make the following assumption. Okay, S4 is greater than or equal to S2. Why? Because to get S4, right, to get S4, you have S2 plus some other number which is either 0 or positive. Okay, so that means it must be the case that S4 is greater than or equal to S2. Similarly, you can show that S6 is greater than or equal to S4, or S8 is greater than or equal to S6, and you can extend this concept to S sub 2n, right, is greater than or equal to S sub 2n minus 2. Now, what does this establish? This establishes that this sequence, okay, S2, S4, S6, S8, and it keeps going. S2n, okay, S sub 2n is actually, it's an increasing sequence. Increasing sequence. So this sequence of partial sums is actually an increasing sequence. So once again, the sequence of partial sums, this S sub 2, S sub 4, S sub 6, S sub 8, and this sequence is a sequence of partial sums, and these partial sums are increasing as n increases. Now let me show that this sequence is actually bounded as well. So let's consider S sub 2n, okay? It's gonna be A1 minus A2 plus A3 minus A4 plus A5 minus A6 plus dot dot dot, then minus A sub 2n minus 2 plus A sub 2n minus 1 minus A sub 2n. That's the partial sum for 2n. So S sub 2n is equal to A1 minus A2 minus A3 minus A4 minus A5 minus A6 minus A7 minus, keeps going, okay, then minus A2n minus 2 minus A2n minus 1, and then minus last term A sub 2n. Now here is some interesting observation. The observation is that this A2 minus A3 is actually greater than or equal to 0. Why is that the case? Is because of this condition. In the condition 3 here, it says A sub n is greater than or equal to A sub n plus 1. So that means A sub 5 is greater than or equal to A sub 6, or A sub 6 is greater than or equal to A sub 7. So each of these numbers are greater than or equal to 0. So this is greater than or equal to 0. This is greater than or equal to 0. This is greater than or equal to 0. Okay? And this is A sub n, A sub 2n is actually greater than 0 strictly, because it says that A sub n is greater than 0, positive terms, each of them, okay, excluding the sign. So look, you are subtracting bunch of numbers from A1. All of them are either positive or 0. All of them are positive or greater than or equal to 0, I meant to say. All of them are either positive or greater than or equal to 0. So that must say that, or from this information, we could conclude that S sub 2n must be less than or equal to A1. Okay? S sub 2n is less than or equal to A1, which means this sequence is bounded above by A1. So this sequence of S sub 2n's is bounded above by A1, which is the first term in the series. And also, we derived that this sequence is increasing. So, you have a sequence which is bounded above, and that sequence is increasing or monotonic. So, by the monotonic bounded theorem, okay, we can conclude, monotonic bounded theorem, we can conclude that the sequence converges. Okay, so let's see, that tells me that limit n approaches infinity, S sub 2n converges, and let's assume that it converges to some number s. So remember, the key thing here is that you have an increasing sequence and the sequence is bounded above by a sub 1. So monotonic boundedness theorem, right? So by that, the sequence must converge to S. Now we just showed it for even sequence, even values of n, right? So 2n, right? What about if we have S sub 2n plus 1? That means for all the odd possibilities. We just showed that it converges for even cases. How about the odd cases? We can do that too. So let's see, limit n approaches infinity, S sub 2n plus 1. Where does that go to? And we can do that pretty easily. Limit n approaches infinity, S sub 2n plus 1 is nothing but, let's put it inside a square bracket, is S sub 2n plus the last term, which is a sub 2n plus 1. So this is very important for you to understand, right? So S sub 2n plus 1 is nothing but S sub 2n plus a sub 2n plus 1. Now by using the properties of limit, we could say limit n approaches infinity, S sub 2n plus limit n approaches infinity, a sub 2n plus 1. Now we just found out that this converges to S, right? Which is right here, we found out. Plus limit n approaches infinity, a sub 2n plus 1 must be 0. Why? Look at this condition, condition number 2 or assumption number 2. Limit n approaches infinity, a sub n is equal to 0. So that guy must go to 0. So you have S. So we just found out that the sequence of partial sums converges to S regardless of the subscript, whether you have an odd subscript, even subscript, or an odd subscript, okay? So it converges for both even subscripts and odd subscripts, and they converge to the same value, S. Therefore, this series must converge to S. So the alternating series test tells you if you have a series, alternating series with the following characteristics, each term is greater than 0 and limit n approaches infinity, a sub n is 0 and a sub n is greater than or equal to a sub n plus 1, then the series must converge. I hope that this discussion was helpful. Thank you very much.